This conference will now be recorded.
Good evening, one and all. I'm A. Rajesh from EC department. My subject is embedded system design. So coming to embedded system design, and first we are going to define what is an embedded system. Embedded system is a computing system. It is not a general purpose computing system. It is a special or specific purpose embedded system doing a special or specific task. It is having both hardware and software. So it is having some peripherals, it is having some sensors, it is having some output devices like actuators. Internally there is a processor. So this is all hardware part. There is some program which is going to control all these hardwares, that is application software. This application software and the hardware are together are controlled by program called RTOS or real-time operating system. So this real-time operating system is going to control the instructions of mentioned by the application software to the hardware, and it is for doing a specific task. So under embedded systems we are having various number of applications. So these embedded systems are utilized in all the applications. So they are all the applications in every sector. So they are becoming reliable servants. They don't require any identity, and they can control as much as load. So they don't require complaint. So one embedded system designed for a specific purpose can do as much work as it can. So you can go on adding applications to it. So this, if you see, these are all the examples of an embedded system, like your digital piano, digital camera, refrigerator, electronic toy, car, satellite systems, and modem, traffic light controller, digital watches, smartphones. So thus embedded system is having three components. It is having a hardware, application software, and a real-time OS. And based on the category of classifications, complexity, and performance, we are having one classification called small scale embedded systems, which may not require this RTOS, medium scale OS, embedded systems, and large scale embedded systems may require this RTOS. The RTOS purpose is just and and giving the priority to the tasks done by application software. And you define embedded system as microcontroller based software driven reliable real-time control system. So I can define my embedded system as a microcontroller based software driven reliable real-time control system. So it has a sensor, it has a to D converter, it has a processor, it has a D to A converter, it has an actuator. Sensor is going to sense the input. It is again converted to digital form by an A to D converter, and the processor is going to process the data. Digital to analog converter is going to convert it to an analog form. Then the commands are given to the actuator, which is actually controlling the output. So this is classification based on the generation, first generation, second generation, third generation, fourth generation. Classification based on the complexity and performance, small scale embedded system, medium scale embedded system, large scale embedded system, on based on the deterministic behavior, real time, hard and soft, and based on the triggering event and time trigger. So these are the applications of embedded system: consumer electronics, household appliances, automotive industry, home automation and security system, telecom, computer peripherals, computer networking system, healthcare system, banking and retail, card readers. So these are the applications where our embedded system devices are available. And the major purpose of embedded system is we have to collect the data by a digital camera. We have to communicate using wireless and wired modems, routers, switches. Then we have to do signal processing. Then we have to do monitoring by some displays, and we have to do controlling of some parameter. Then we have to use application specific user interfaces such as buttons, displays, keypads. And the characteristics of embedded system are, it is single function, tightly constrained, reactive and real time, microprocessor based, memory, connected hardware and software. Coming to components of embedded system, as I told, the hardware part, your embedded system is a combination of hardware and software. The software is an application software and a real-time OS. Hardware part, it is the core of the embedded system, that is called a processor. This core of the embedded system, is going to control all the peripherals like sensors, actuators, A to D converters, D to A converters. So the processor can be a general purpose and domain specific. You can use a processor, you can use a microcontroller, you can use a DSP, you can use a ASIC called application specific IC, you can use a programmable logic device, you can use a commercial off the shelf component. So if you are designing an embedded system for a electronic toy, you can use a 4004 processor or microprocessor, microcontroller. If you are designing any missile control system or time critical systems where your output must be deterministic, you can use an application specific IC. Application specific ICs are one which are designed specifically for doing that purpose. And you can also use PLDs and commercial off the shelf components. So coming to general purpose and domain processors, the microprocessor is a CPU. The initial processor is an Intel 4004. It is having 1K data, 12-bit program counter, 16 4-bit general purpose registers, 46 instruction sets, and you can design the processor in two different architectures. One is hardware architecture, another is von Neumann architecture. Hardware architecture is having a separate bus for data and program memory, whereas von Neumann architecture is going to share a single bus for both data and program memory. Also, you can classify your architecture based on the instruction set as a RISC and CISC, reduced instruction set computing processor, complex instruction set computing processor. So general purpose versus application specific. General purposes can do general computational task. It contains a CPU and control unit, whereas the application specific integrated circuit is having an architecture with instruction set of a specific domain. Also, this microprocessor can be a general purpose or an application specific. Coming to microcontroller is nothing but a CPU with a scratchpad RAM and a general purpose timer. Compared to microprocessor, it is cheap, readily available, cost effective. TMS 1000 is the first microcontroller, and various vendors like Philips, Atmel, Maxim, Microsim, they have generated. And mostly all applications we use Intel 8051 microcontroller. It is a general purpose. So we will differentiate what is a microprocessor and a microcontroller. Microprocessor is nothing but a CPU having arithmetic and logic unit, whereas microcontroller is a CPU with a scratch pad, ROM, RAM, flash memory. It will have interrupt control unit. It will have timers. Your microprocessor is a dependent unit. Your microcontroller is a self-contained unit. Microprocessor is used for general purpose. Microcontroller is used for an application specific. And performance wise, we will be targeting high-end market for microprocessor, and this is not so critical. And we can include power saving techniques in microprocessor. Microcontroller has uh, uh, less utilization of power, and lot of power saving is done here. limited power saving options are available in microprocessor, whereas lots of power saving is done in microcontroller. Coming to the next hardware part, first one, you can use the microprocessor, you can use the microcontroller. Next is the DSP. DSP is nothing but a digital signal processor. In order to meet the demands and power constraints, we produce a specific DSP processor. Its architecture is designed specifically, and it is 2 to 3 times faster compared to other devices. The key units available in it are program memory, data memory, computational engine, and input output unit. So as I told, your processor can be classified into two types based upon the architecture, RISC and CISC. What is RISC? Reduced instruction set. What is CISC? Complex instruction set. So reduced instruction set and complex instruction set. So as we told, it is reduced, it is having less number of instructions. It is following instruction pipelining and it is increasing the execution speed. What is instruction pipelining is, whenever we fetch an instruction, we do processing and we get the related data and we store in the memory, and after that we do processing. Again we retrieve the data from the memory and we'll store the result in final in the memory. So this fetching, doing the processing and storing in the memory, this all operations are done for one specific instruction. Whereas if you go for pipelining method, in pipelining, first instruction is processed. At that time, we will be doing fetching of the second instruction. When first instruction is in the execution state, we will be doing the fetching of third instruction. Second instruction will be in the execution part. Third instruction will be in the storing part. So like that, pipelining means we are going to parallelly allocate certain space and time of the processor to do multiple instructions at a time. One will be in the fetching state, one will be in the execution state. Like that, the speed of the processor increases, and this is having orthogonal instruction set, and a large number of registers are available for this because we have to save the data in temporarily in the registers, and again we have to do fetching, execution. So for that we are having large number of instructions. Your programmer needs to write more code if he is using the RISC architecture, and the instruction set followed is a single and fixed length, and it is having Harvard architecture. Okay, Harvard architecture means we are having a separate bus for data memory and program memory. If you're following a CISC architecture, it is different from the RISC architecture. We are having greater number of instructions. We are not following instruction pipelining. We are not having orthogonal instruction set. We are having limited number of registers. Programmer needs to write less number of code in the desired task, and the instruction length is variable. So see here, RISC is having less number of instructions, CISC is having greater number of instructions. RISC is following instruction pipelining, CISC is following no instruction pipelining. Here it is orthogonal instruction set, here it is non-orthogonal instruction set. We are using large number of registers, we are using less number of instructions. Here we have to write more code, here we have to write less code. Here it is a fixed length instruction, here it is a variable length. Here it is a Harvard architecture. Means Harvard means we are having a separate bus for memory as well as data memory. Program memory and data memory. Whereas CISC architecture can follow Harvard or von Neumann, depending upon the processor design. The CISC architecture having can utilize either Harvard architecture or von Neumann architecture. So we are seeing what is a Harvard architecture and what Neumann architecture. Harvard architecture is having separate buses for instruction and data fetching. See, your processor internal, it is having a logical unit, arithmetic unit, some memory control unit. So arithmetic logic unit, they are going to do some operations. So for that, data is fetched from the memory, instruction is fetched from the memory, instruction is decoded. So whatever the instruction is fetched, it is decoded, it is kept in the memory. Then based on that, it is processed it. Again, the result is stored in the memory. So for that, Simultaneously, you may require data from the memory for instruction as well as data. And if you are using separate buses, it comes under hardware architecture. If you are using a single bus, so how you can use a single bus? You are going to delay the operation. So you are going to fetch the instruction, then using the same bus, you are going to get the data. So if that is called a von Neumann architecture. So as we are using separate memory, separate bus for instruction and data fetching, separate buses for instruction and data fetching, you can call this as a pipelining method, because we can do execution stage as well as fetching of next instruction by using separate buses. So as it is doing pipelining, it is becoming faster, high performance is achieved, and physically you are keeping two buses, so it requires high cost and no memory alignment problem, and they are having these memories located in different places. But as in von Neumann architecture, you are using a single bus, you require it requires less performance and cheaper, and you have to do self alignment modifications, and this data and program memory are stored in the same location. Sometimes accidentally data may get corrupted. So your processor is categorized based upon the architecture as von Neumann or hardware, and based on this they are classified into RISC and CISC. One more classification of processors is Little Indian and Big Indian. So Big Indian means it is easier to determine a sign of the number, and it is easier to compare two numbers, it is easier to divide two numbers. Whereas Little Indian, addition and multiplication of multi-precision numbers will be done. So the main core of an embedded system is a processor. That processor can be a general purpose or can be a application specific. So what is application specific is, depending on the vendor, he can design his own IC, and he can create, he can customize, he can do the designing of the hardware for generating a faster device, less power, high speed, less area. So such requirements can be met by ASICs, application specific ICs, and that depends upon the purpose. So these ASICs can have different architectures such as gate array architecture, standard cell architecture, or full custom designing architecture. So the third one is programmable logic devices. Your core of the embedded system can be a PLD. These PLDs are programmable logic devices. They consist of an array of gates. We can just program it as per the requirement. So these PLDs are categorized into three types: ROM, read-only memory, because embedded system itself is nothing but hardware software. Based on the software written, hardware will operate. So the user cannot alter the program, nor he can alter the device's hardware. So a ROM, read-only memory, it consists of code written in it in terms of its locations, data. So whatever the architecture it is using, read-only memory, if it is based upon the transistors switches, based upon the data written in it, some of the transistors will be on, some of the transistors will be off. So data, it is written, so no one can alter the data. Only thing is, your embedded system, once it is switched on, the processor is going to read the contents of the memory, and as per the instructions given by application software, it will just operate. Next, the second classification is programmable array logic. Third one is programmable logic array. So we are just programming it. So this is related to ROM. PAL, programmable array logic. So your core can be a PAL. It has a programmable AND array and fixed OR array. So your hardware, if you want to design a half adder, full adder, some logic. So the arithmetic and logic unit you can create in terms of PAL by using a programmable AND array and a fixed OR array, and all sum of products forms can be implemented here. Another classification is PLA, programmable logic array. It is having both programmable AND plane and programmable OR array. So there is one more classification called FPGA versus CPLD versus microcontrollers. See, these processors, we can use a processor, general purpose processors, or a microcontroller, or an ASIC. So it is application specific. But there are some designs which require some more complexity compared to PLDs. A PLD consists of a ROM, PLA, and PAL. So, but you require some more complexity, but you don't want to create your own IC. So then there is a standard IC called FPGA. It is called Field Programmable Gate Array, and one more complex PLD. So from PLD, architecture complexity increasing to CPLD, and totally the design of the architecture is different in terms of an FPGA. So FPGA is having configurable logic blocks. It is having input output blocks. So whenever you want to configure this IC, you can keep in a socket. You can dump your program into an FPGA or a CPLD. So your microcontroller is a smallest design of your core. So then from that you can go for slightly complex. If you want to go, you can go for CPLD. If you want to create still more architecture and faster hardware, you can go for FPGA. Or if you want to go for a unique design, you can go for an ASIC. So flexibility point of view, FPGA is more flexible compared to CPLD and microcontroller. FPGA logic is stored in terms of lookable tables, lookup tables. Lookup tables is nothing but a ROM where the input is selected as an address, outputs are stored in the memory. Complexity wise, it is more complex compared to CPLD. Then it is not a computing system, it is just a hardware. Processing speed is more compared to CPLD and microcontroller. Commercial off the shelf component. So what is this commercial off the shelf component is for most of the devices, like we want to create some Wi-Fi for our laptop. What you do is you can get a wireless Wi-Fi for your hardware, CPU or laptop. You can just use as a single device. You can insert it and it will act as a Wi-Fi device. So the hardware and software already it is existing. The design is available. Licensing will be provided. Just it will connect to the specific devices. So what is the purpose is controlled by one software. So that is your embedded system. So once again, I'll define it. Embedded system is a combination of hardware and software doing a specific task. And for doing this specific task, the hardware is specifically selected, the software is specifically written, and for writing the software and you require an application engineer, and this all is controlled by a real-time operating system. And your embedded system is available in our all day-to-day life in many number of applications. We are going to use these embedded systems. Okay, thank you. We'll see in coming classes.